You want to record this? Be my guest. Just tell me your name and we'll do it. Okay. Have you heard that the morning class of assembly, it was a long session. I think I wore out everybody. We did a lot of stuff. So you may have heard that in the discussion chat room. Okay. We're going to get started soon. It's 2:03. What do we have? Okay. So, hi, let's switch the cameras to the other one. Where did it go? Here it goes. Okay. So, we have next week. Oh, it's getting awfully close. Next week is big midterm. The last class, which will be the last class meeting before the spring break. Okay. And so that puts it on a Thursday. And we'll save the live programming test till after midterm. Right now, it pays to concentrate on this one here. Last class before spring break. Okay. Who asked me? Anybody else to record this? Okay. Look through all the names. Somebody asked me, I'm going to be away from California. I'm traveling during that week. Do I have to cancel my trip for this? No, you can go on a trip. Just make sure you can connect internet. Just make sure you can receive email at the time of the test. That's all it requires. I'm going to email you an attachment that is a copy of the test questions. Then you write the answers into the same copy and email it back to me. So I'm not asking you if you're in California or if you're in France. I don't care. Just be sure you can receive email wherever you are, and everything's cool with me. In fact, I think it was a semester ago, a couple of people did the whole semester in India and never came to the United States, and it all worked fine. You don't have to be near Fullerton to do the class. All right. Well, so what do we have here? You should. I mean, these are good people, but they're getting paid too. So you got to take them some work to do. Make sure you, when you have an issue, a program that's crashing, or you just want tutoring about what happened in the lecture, email either one of those and see when they have free time. And I think they'll do their best to make time to teach you tutoring assistance or debugging assistance. Okay. All right. And then after you finish this class, you can have the job that they're doing. Just apply for it and you'll get hired, because like in the rest of the world, when they're looking for assembly programmers, they get very few applicants. So whoever applies just gets the job anyway. You apply here and say you want to be part of the assembly debugging team, you'll get hired right away, because nobody else wants to. Okay. Let's see. What else do we have for announcements? Here's one thing let's be very sure of. Um, on test day, I don't read PDFs, so don't send me a PDF back as part of your test. I don't know why students do this in the past, but I send you a copy in open source format, and I write on the test, it's okay to send it back to me in the same format or DOC or DOX CX, but no PDFs. And guess what? 5 people send me PDFs. I don't know why. They have to do this for some reason. I can't understand it. But the test will say clearly on the front page, please send me the test back with your answers in one of these 3 formats. And then it says no PDFs. And now 30 people will get 5 PDFs. So I have to throw them out. And then some people get 0. And they say, why'd you do that? Well, I thought you liked PDF more than those others. But the front page says no PDFs. Oh, I don't read the front page. What do you think I'm going to do? So everybody's in the room, in the Zoom session now knows teacher doesn't accept PDFs. What else do we need to know about the test? I think 2 hours should be enough. 2 hours, that's from 2 p.m. to 4 p.m. When I have the test fully created, then I'll have a better estimate if you need more time. On programming, I often in the past ran it for 3 hours. So it would go from 2 p.m. to 5 p.m. And if you have a class that follows this one immediately, then you should contact me 3 or 4 days in advance, and I'll make some arrangement for you. I'll try to work out a plan for you. So, but this is programming usually. Programming takes time. Okay. Incidentally, isn't that cool? If we were in a fixed classroom, I can't give you extra time because the next class coming in wants their chairs. But here you've all earned the privilege of remote testing. You can take your test in New York and it's okay with me. You don't even have to tell me you're in New York. And if it looks like a hard program, then I'll give you extra hours and we aren't kicked out of a classroom. Okay, let's get on to today's business. Let's see, what is our big topic? Okay, we're going to do the, let's see, is that right? Let's go back. I did this a little bit many weeks ago. We're going to do it in serious detail now. Memory management, or memory organization, if you like. Same thing. Okay, on the side here, we have a function. Maybe that's main, and main calls function A, and A calls function B. So you have that image in your mind. Ordinary programming functions, and think in terms of C++ for the time being. All right, and then we want to know what happens in memory when all this is going on. Okay, so here's a start. In memory, we're going to draw it as these quad words. So imagine steps across here. Each one is a quad word, and each one has 8 addresses, but we usually only show the lowest address out of the group. So if this was Yanny 4B70, and there's a lot of leading digits that I truncated, then this would be the byte here, and the byte right next to it would be 4B71, and the one next to that 4B72, and all the way across until the last one on this side is 4B77. Okay. So there's each byte in the quad word has its own address, and to save space on paper and on diagrams, we usually give just the address of the lowest numbered byte in the whole quad word, which is typically on this side on the right, this one right here. That has this address, and the one on all the way across has that address. Okay, so I should watch and see if there's messages. Would we have to be on Zoom? The answer to long is no. You don't have to be on long. This is a take-home test. You don't have to have Zoom on. You just have to be able to receive the email that brings the test copy to you. Okay, so a function like main starts up, and C++ allocates an activation record. That's a segment out of memory. So I'm just going to draw one and say this is it. Okay, inside that box, that's our, just trying to highlight it where it is. Like so. Okay. So the purpose of the activation record is to store the values of all the data that belong to M, to function up here. So it is a contiguous region of memory used to store the values of data owned by a specific function. The data that are declared in A don't count. They're not in here. Just the data that's declared inside of M. Yeah, let's put this on the record. And I'm going to write AR for short. AR, you know the name is activation record. Online, it's often called stack frame, which is exactly the same thing. Okay, two names for the same thing. And what is it? It is a region, G-I-O-N, region of memory where one function stores the values of its data. I don't know of any other reason, other purpose, stores the values. Its data. Okay, so if a function is declaring double some name over here, cost and float something else, A and integer B and long integer C and char D. At declaration time, they don't have values. Let's say it's like that. Or you could give this one a value. Doesn't matter. C and C++ goes through this at startup time and counts the number of bytes necessary. So this would count as 8, and this would count as 4. This counts as 4. This counts as another 8. This counts as 1. And it adds it all up, 24, 25 bytes needed My bet is that it's going to round it up to the next highest quad word, which would be 32 bytes. Yeah, my bet is this going to allocate 32 bytes in the AR. And C++ already creates that AR at the moment your first function starts. It looks ahead and finds all these. So some of them don't have data yet. It will have just electronic garbage in the place. But there's a place set aside for it in advance where this, for instance, this B will eventually have an integer stored there using 32 bits. Oh, okay, let's give some names, some terminology. The quad word in an AR with highest address ADD or ESS is called back end of the AR. And you can guess the other way around. The quad word in the AR with the lowest address is the front end. Also, Q word with, there's the key, lowest address is front end. Okay, let's draw that on the screen. And let me make my visible. Okay, let's draw a picture of that. And here's the very last quad word. Way back there, if you have 8 gigabytes of memory, then that one is the last one before you fall off the end of your memory and you don't have any more. So I've noticed that it seems like it doesn't always put, the machine runtime system, it belongs to the operating system, doesn't always put the activation record at the very, very physical end of memory, but pretty close to that. So here I'm going to draw a quad word. Here's a quad word here. Excuse me, I'm going to draw an activation record. Okay. So this green area is a quad word at the back end. And the red one will be the quad word at the front end. And those two have special uses, and I'll describe them in a few minutes. Okay, so let's go on to say that the back, before I do that, activation records are classified as either inactive or active. AR is active or inactive, which simply means that if it's active, the function that created it is currently updating its values. So an active AR is currently in use. There's a function running that's actually changing values in it. Active AR is in use. Okay. An inactive one is dormant. It's sleeping, and it comes. I'm going to show this new diagram. Okay. Here's an AR made by an outside function whose name is M. And then after a while, M calls another Q, another function. So Q gets its own AR here. Where's here's the front of Q's. This is the front of M's AR. And this is the back side of back end of Q's AR is the back end of M's AR. Okay. Now, but let's pretend at this specific moment, Q is executing. Therefore, Q has an active AR. M is not executing. Its AR is inactive. I put that there. Inactive. And this one is active. When Q is finished, then M will resume execution, and then this will become the active one. But at any one time, only one AR can be active, and that's the one currently in use. That's a given fact. Only one AR is active. So if M called Q and Q called R and R called X and X is running, then there's 3 inactive ARs and one that's active, the one that belongs to here. Yeah. So only one AR is active at any time. All right, so we know the back end. We know some more. RBP is the signal flag that marks the back end. So up here, this back end has some address, 3F80. That number is stored in RBP. That's the address of the back end. And the address, if it's the active record, if it's an active one, the address of the front end is in RSP. And RSP is always smaller than RBP, so it'd be maybe 3F40, like such. Okay. Notice how RSP is smaller than that one all the time. Occasionally they're equal, but RSP is always smaller, has smaller address. The small address is at the front end, high address is at the back end. Okay, so in the record book, you put RBP holds address of the back end. And RSP holds address of front. Okay, some more facts. When C++ is in charge of all this, it always starts the back end on a 16-byte boundary. Let's see, even assembly, I'll discuss that in about 15 minutes. Assembly works slightly differently, but awfully close. So C and C++, back end is always on the boundary. Okay, no exceptions. When it's active, this is picture right here. Back end ends in 80. The front end is also on the boundary until the moment that another function is called. Okay. So front end is on boundary all the time. The function is executing. The function executes. However, at the moment that function calls a new one, a push happens. But when, and puts it off the boundary, when another function is called, there is a there's right out push RIP, which one more push of a quad word puts it off the boundary, puts the front end off the boundary, which puts front end off boundary. Okay, let's see. I'm going to draw that into the picture and see if I can do it in a blue color. Back here, here's the picture. Back end, it's on the boundary. On the boundary, you can detect that because it ends in 0. That's a dead giveaway. Front end, this is executing, being updated all the time. It ends in a 0. It's on the boundary. This function that's using this AR decides to call a sort function, something else. Then at that moment of the calling, there's a push. I wrote it here. And the value in RIP is added to the front end. RIP. And what did that do to the addressing? The addressing is now off. This place right here is now 3F38. Okay, so, and then it goes dormant because the new activation record is going to take over and be created down here somewhere. Okay. So when a call happens, there's this push RIP, and then it goes dormant or inactive, and I want to put a marker around it. Do I have a, I need another, I don't have more colors. Okay. So I'll draw a brace to show it. This is the dormant activation record from here out to here. It goes to sleep, and the system starts a new activation record directly below it here. So how does C++ know what to create? This is, I want to put a green marker for the back end. Let's do it right here. That's the green back end. Creates this AR, and then there's a red front end. Right through there. Okay, and this is new AR. So if this RIP is off the boundary, the back end is going to be, this is cool, on or off, 3F30. The new one starts at 3F30, which is on the boundary. And I think I had that sentence somewhere that all activation records backends are on the boundary. Did I write it down? Oh, here it is. without fail. There's no exception. The back end is always on the boundary. And in this little diagram, that's exactly what happened. This one that's executing has front and back on the boundary. It gets this extra RIP, and then it's automatic. The next quad word is going to be back on the boundary, and that forms the new AR down here. How does C++ know how much space to give it here? Well, it adds up all those data declarations, all the stuff you declared in the new function, like a bunch of these. Even if they don't have values yet, it still sees that your program has declared all that. And so it has created enough storage area here to keep all those variables. Okay. Looking at, see if there's some questions. Okay, no questions. Okay. Let's try. Oh, we're going to add. We're going to give more detail to the picture. So I think I need to start finishing the picture. Let's take doing black. Okay. Here's an AR. Okay, and we used. Let me just see. Yeah, okay, we'll use the same color scheme here. This is the back. And this is the front. The function is executing. We'll give numbers to these guys. Yeah, I'll just use the same numbers. It was 3F80. 3F80. And then it was 3F40. Okay, and for this is active right now. The back end is stored in a register you've heard about, RBP. And the front end is stored in your other friend. They mark the front and the back of this activation record. Okay, we're coming. Now you know this function is going to call a new one. So it's going to, the call statement includes within it the push RIP. And what color did I use previous for that? I think it was blue or something. Doesn't matter. I'll put it in blue. Okay. So we're pretending the function that owns this activation record is now preparing to call another function. So part of that call process is to put in here RIP. And it's a push operation. Therefore, RSP has moved up to that one. 3F 38 RSP. Okay. Now the system, the operating system has a function that calculates how much space is needed. So it goes down here, allocates this. Okay. Now, let's see. In your assembly program functions, in your assembly programs, after you go through segment data, segment BSS, segment text, what's the first statement that executes in assembly? You want to guess? Can we leave this for Johnson?
All the pushes or the what's it called, the GPRs?
Yeah, you're right, but we just want one. You
Oh,
give
the name of the
which one?
file. So it would be like,
What's that first statement? First executing statement. You're close, but 16 of them is too many. We just want one. Right, Richard's
push.
on top of
Okay.
it. Okay, there's part of the call is to push RBP. And so
Okay.
here's RSP pointing here. RBP shows up here. And what is it? It's 3F80. Now, because it was a push, RSP is now here. Okay. That's an R. Okay. That guy's address got put into here. And I should emphasize there's an invisible boundary here. There's an invisible separator where the last activation record ends and the next one starts. The last one ends with the RIP. The next one, it's in your source code of your assembly functions. The first statement is push RBP, and that's starting your activation record that belongs to your assembly function. If it's C++, C++ performs that for you. C++ does a push RBP. Okay, so it's that in the first place, and RSP is here. What is your second executing statement in assembly? Richard, what does your program say? The second statement in all of assembly. Yes, that's it. Move into RBP, RSP. You misspelled it, but I know what you meant. Right. Okay. So there's a move statement. It says right now, RBP is still holding this one, but it says copy into RBP this address down here, which I can mathematically figure out. It's equal to 3F30. It's 8 less than the one above it. So there's RSP, and the second instruction says copy that number into RBP. So in picture form, that says RBP is also here. Okay. And I actually did something out of order. This isn't allocated until the step that's coming next, but it's okay. Okay, and C++ will now count up all those bytes that you've declared and add it to RSP and put RSP here. And you see what happened. In the old activation record, RSP and RBP bounded it front and back. In the new one, RBP is the back and RSP is still the front. It's set up again for a new activation record. I want to mark it in green. So the back end is here, and in red, the front end is here. The calling a subfunction involves moving RBP to be at the back end of the new AR, and RSP moves to the new front end. Okay. Now this is a description of how C++ works, and C. Okay. Assembly is slightly different. It doesn't jump this all the way down here automatically. It allows you the freedom to push what you want and what you don't want. Okay. But in C++, it allocates all this space based on what you've declared in the function that's starting up. Did we where I had all those data types written out? I don't know what I did with them. If I can still see them. Yeah, if your function declares all these, C++ is going to add up how much size, how much storage they need, and then move RSP ahead by that amount. And there your activation record has been created. Yes. Okay, let me watch our time. At 3 o'clock, I want to make a switch over and we'll do something live on the machine. Okay, let's study what happens in reverse. In reverse, your called function reaches this statement. Okay. Part of executing a return in C++ is to, let me see if I remember it correctly. Well, there's a, okay. I hope I get them in the right order. There's a pop RBP. We have to reverse the call. That's not very good, is it? Do I have a good, better? We have to reverse the call, and there's a pop RIP, and right here there's a move R. It's the reverse of that other move, RSP, RBP. Yeah, I think that's it. See, in the high-level language like C++, we just write return, but it compiles into 3 instructions. I'm pretty sure we'll walk through it and make sure. I think this is it. Okay, so imagine this picture. The activation at the top belongs to function A. It calls function B down here. That's off a marker. I'll better get rid of it. Okay. Function B is finishing now. It's going to conclude, and its job is to put back everything where it was, restore everything to its former location. I'm trying to see if I can, is this right? Not very well. I don't have a good blue one. Okay, so it reaches the return statement. Now let's walk through in the diagram what that means. Okay, so RSP is at this front end, RBP is back there, RBP previous is stored at that place. That's back end in green, front end in red. So your program in here executes return. That performs this move. RBP is pointing here, and you put it into RSP. You see what's happened. RSP is no longer here. RSP is pointing back there. You have 2 of them pointing to the same place. Got it so far? Then there's a pop operation, pop RBP. Pop obeys what RSP is. RSP is pointing to this thing right here, 3F80. It pops it into RBP. RBP has jumped back to here. RBP is no longer pointing here. It's restored its value to here. Next one. After that pop, RSP is not at this green back end anymore. It's now back here. So there comes a pop RIP, and that takes this number inside of here and puts it back into RIP. Next, execution address. So this one pops off, it goes into RIP, but how did it get there? It's the next thing to execute below the function call. So the caller function can resume at the very next statement right after the one that made the call that did all this activation record below here. Okay. So that one gets popped off. A pop moves the RSP, and now RSP is back here. Isn't that nice? It's those two registers are bounding the activation record that was previously in use, and now it's reactivated again, and A can continue to execute to its own end. Done all that? Okay. The calling and return are quite remarkably programmed for other high-level languages. It just, they got it all figured out, how that when a call comes, it creates a new activation record, it moves RBP to the back end, it moves RSP to the front end, it does some work, and then when it says return, it undoes all that it did. Here's the reverse, here's the reverse of that move, here's the pop, and here is restarting the caller function where it left off. Okay, so some things we can take out of this is RIP. Okay, for an inactive activation record, RIP is the front end. RIP is at, no, that's the wrong word. It is stored at the front end. And it only applies to inactive ones, of inactive AR. That's always true. Okay. And what else can we see? The back end of any activation record, including the active one or the inactive one, the back end holds the address of the previous activation record's back end. That's right here. That address right there is stored here. That's the back end of this one. The back end of any activation record is the address of the previous activation record's back end. Stored in back end previous AR's backend. Okay, that'll always be true, whether it's active or inactive. They all get it. Here's an interesting sub footnote. What about the very first activation record for which there's no previous guy? See, the very first one that starts, it's usually the one that belongs to main. It has no previous one to store there. The answer is the system fills it with zeros. So if here's so you're running main in C++. Okay, and of course it's going to create an activation record, and it has a back end. What do we use? I think we use green for the back. There's a quad word back here, and there's a quad word at the front end. Okay. Okay. The rule is that the back end stores the address of the previous activation records back end, but this doesn't have a previous, and so we can watch it live and see that this is all zeros. 0 is like a null pointer. It says there's nothing there. So it will fill with zeros. All right, so that's footnote to the main principle is written here. Okay. All right. We'll return to some of this again. You got to wrap your head around it and make sense of it. If the test question says, when C++ executes a return statement, what happens in memory? Then you've got your head around this, and then you give me these 3 things as the answer. It first moves this move, and then it does this pop, and then it does this pop, and then it's returned back to the previous activation record. Okay, I think we're close to the 1 hour mark. Let's switch. I'm going to try and show you this in live, what we just did, and see how much of this we can accomplish. Any questions before we go to, yeah, okay. Let me get the, okay, along the way, you're going to see, and you're starting to learn GDB. Okay, so this is, what could we call this? Lab time or something. GDB stands for GNU Debugger. It's a world-class product. It's used commercially, it's not just for educational institutions. It's a professional product that is used to debug programs in many languages. I don't know the count. It's like 15 different programming languages can be handled by GDB. So it is really professional debugging tool. All right, what do we need? We're going to run it right now and use it to look at the stack. What we need is we have to modify the bash file. In a small way. Every one of the compiling statements, G++, -C, -WALL, the whole thing, somewhere in there you have to attach a -G. Okay. And in the linking statement, you attach a -G. G++. You don't put a C for compile if you're linking, but you put all this other stuff. -standard equals C++ 2A. It's the newest one I know about. And all these O files are here, but at the end of it, you put G. Okay, and it doesn't have to be in that order. You can flip them around and it's fine. When you come to execute, you write GDB as a prefix, GDB space dot slash my program dot whatever. Okay. So I usually make 2 bash files. The first one, which is a regular execution, and then a second one, which has all these attached to it. This, and you put this at the end of it, and you have to put this in. Okay. Then you'll see that in a moment. What the G is doing, it's enabling debugging mode in your program. It's for the debugging mode is for the developers only, not for the customer. You never ship the bash file for GDB to the customer. You only ship the ordinary bash file to the customer. Okay. What else do we need to know? And we'll do it. I guess we'll probably only get through C++ style at the moment for today. Debugging tools are famous for breakpoints. That's a place in the source code where you indicate you want to execute there to that point and pause. Okay, and you'll see, let me do it in a moment. It's the letter B for break. And if it's a simple single file program, you don't have multiple ones to link together. You just simply say break followed by a line number, break followed by another line number, or you can say break followed by the name of the function, which is probably going to be main. Okay. Those are instances of setting breakpoints where it will execute rapidly up to that line number and then it just pauses. And then the continue command will tell it to execute to the next breakpoint and then just pause. Okay, so you are all supposed to get to professional level of proficiency in GDB. Today is the first exposure to it, unless you've taken this class someplace else. I think, it's time to actually do it now. Let me find my, I had picked out a sample program, but I got to go find it. Okay, let's find here. Okay. Don't just stay with me until I find this program. And teaching here. No. Okay. It's, I found that it's got, I gotta get it over there where I can share it. I think we're getting close. Okay, let's make the share. I'm just gonna share the whole window. Okay, let's do. It's small font, I realize, but can you see that there's one bash file right there and one bash file here? They're different in the sense that one has a G in it and one doesn't. So let's make a terminal. Okay, so the ordinary one is run. If you make cat on it, you'll look at it as H. This should look pretty much like standard stuff. Nothing special here. And here is the execution, the standard style, nothing special there. But the other one, we'll look at it quickly, cat rg.sh. And this one has G here, you notice, and a G here. And this prefix, GDB, goes to the left side of the usual execution statement. That's the only difference between the two. And this is a comment down the bottom. I don't know what it's doing here. Okay, so to run a program in debug mode, you need this extra -G. And again, it could have been inserted in the middle someplace. It doesn't have to be on the end. That's not important. Okay, got it, everybody? All right, so next, this is really cut down and simple illustration. Here's a C++ is supposed to be demonstrating arrays. Oh, by the way, text editor. I think this is okay. That's not very dark, is it? It's because the color coding changes the stupid stuff. That doesn't help any at all. Okay, And we'll do the best we can. I made up, there's just made up stuff here. Here are some arrays. And we're talking about activation records. These are static arrays. A static array is one whose complete size, not its data, but its size is known to the compiler at compile time. It's not, here's the wrong answer I get every semester is, the test question says, describe what is a dynamic array. Oh, it's an array that keeps changing its size. It grows as you need more space. That is so wrong. It doesn't change its size. A dynamic array is one, here's one down here, whose size is not known to the compiler. It is created during runtime. That's a dynamic array. An array, all of these are static ones because their size is completely known to the compiler, and it can make the activation record of the correct size to accommodate all that stuff. Even if I don't have one, but even if I had one that was not initialized, like where's my thing going? Here it is. Oh, it doesn't matter. Double space GH square brackets 15. Period. No data yet. Ooh, but I better spell it right. This one. Okay. No data yet. The compiler can still figure out that you're going to need up to possibly 15 times 8 bytes of data. And so that's a static one. And there will be space in the activation record for arrays like that that haven't even been filled in yet. That may come during runtime, but the machine doesn't care. It cares about allocating the right amount of storage in the activation record. Okay, I'm going to take that out now. That's not the original. Okay, I'm going to run this in the ordinary way, and it's going to tell us the address where each array starts. Okay, so let's go. I don't know what this does down here. Static casting. This is off the subject. It's taking the address of F and casting it to, I'll just figure it out later. Sorry, everybody. If I start figuring that out, I'll be off the track way too long. So we need a terminal. I thought I had a terminal open, but all right. ls-l and ordinary run shrun.sh, and we need it bigger. Let's switch this. Oh, that's okay. There's those arrays A, B, C, D, and E. There's the first element in each of the arrays, and here's their location where each one is stored. They're not far apart. Notice that their address coincides most of the way until about there, and then it might be different. But these arrays are stored very close together with each other. And I'm going to write down that number. Let's take A, for instance. A is at, I'm putting on a scratch paper, but we can compare it later. 7FF DEA 30C 7B0. Okay. And all of them are very close to that. I'm going to show you that that's actually inside the activation record that belongs to this C program that has only a main function. That's all it has. Let's go to the other one. SSH, what was his name? rg.sh. Okay, so this is running in debug mode. And down here at the bottom of the window, it's asking for some commands. First thing I want to do is make it break at main. Okay. And I don't know the line numbers, but just for the fun, let's make it a break at line 22 and break at line 33. And then look at our save breaks. So it tells us that in this function, we have breaks at 17, 22, and 34. The numbers are way over here on the right side. There's 17, 22, 34. All right. All right. Whoops, I didn't want to do that. Let's run the program. Okay, but it's going to stop as soon as it sees main. Oh, so it stopped where main is. And it says, I'm going to execute line 17 next. So letter N represents next. So I'll press N. It executed that statement, welcome to GDB. And now it says, I'm going to do this other thing next. Okay, so do that. It outputted some stuff. And then it shows line 21. I'm going to execute that next. Okay, this is going to put the space for A has already been created. But now this will put numbers in there. You know, I should have used more simple floats because these are going to be hard to recognize. But we'll do it anyway. So next, we say next. And then it tells us line 22, it's going to execute the filling the array B with its numbers. But I'm interested in A. Let's find out where is A stored. B/X address of where's my something happened here. I lost the focus. Address of A. It says that the array A is stored at DEB0. Bunch of F's in front. That's too much. And what did I write down? DFF. Well, that didn't make sense. Oh. No, that was, oh yeah, I see. No, this is my previous one. I don't agree with. This is accurate. This says that this array starts at address. Now, I'll just give you the last 4 digits. DEB0. Okay. So what is the? We are there. Did that again? Keeps losing the focus. Okay, you remember that RSP and RBP are front and back ends. So let's check those. P/X $sign R. This would be the large number. And if you look closely, it's somewhat larger than the location of A. And then we do RSP. And you notice this is a smaller number, and it's smaller than where A is. A is the top one, and this one is a little bit smaller. And so A is caught between those two. And let's see what B is. B doesn't have any data yet. B is stored at this number. That's larger than RSP, and it's less than RBP. Visually, you can just see that if you focus on the last 4 digits. So B doesn't have any data yet, but it still has its location that the system knows about. And there's one that's coming like C. Let's just change, whoops, that was B. Change it to C. Okay. C is declared very close to B. It's just a few bytes away. is all, in fact. Okay, so let's try this. Here's the formula for counting the number of quad words in the AR. It looks like P/X. P is a command for output, X is for hex. And then we subtract the large number minus the small number. $sign, RBP minus $RSP, quote. Now, that alone is the number of bytes between those two front and end, front pointer and back pointer. But more interesting is the number of quad words. So we divide by 8. We're getting quad words, but we're off by 1. And that's because both of them are inside the count area. When you subtract them, if you had painted on the floor the squares 3, 4, 5, 6, and 7, and you put a marble at 4 and a marble at 6, and you say how many squares are involved, you might say 6 minus 4 is 2, but that's wrong. The number of squares involved are 4 and number 5 and number 6. There's 3. So this is off by 1. And I correct for it. You know what? That's a hex number. Let's do it in decimal. It's a correct value, but it's decimal. B. Okay. What is 25? 25 is 2, 32, 37. Yeah, it says 37. Okay, so there's 37 quad words. So now we can look at them. It's X/37 quad words. And we show them in hex output. And G is for very, very large. Okay, and they start at RSP. Okay, oops, no space here. That's our activation record. And the way you read it, instead of one column, the people who made this split it into 2 columns. See, this part is the quad word stored at DE20. And this part is the quad word stored at DE28. This is the quad word at DE30. This is the quad word at DE38. So to save vertical space, they put it in 2 columns. If we went to here, this is what's stored at DE-A0. This is stored at DE-A8. Okay, so that's 37 quad words if we count them out. Notice it didn't come out even, so this one is left off by itself. Now, where was A? A was located here at DEB0. DEB0. That number is the first number in the array called A. And I know you've forgotten what it was, but let's go back here. Here it is. The first number is 2.2. And the next number is 3.3 and 4.4 and 5.5. It's going up by 1.1 each time. Okay, so at A, DEB0, DEB0, this is 400 exponent is 2.0. And this is just a little bit larger than that, 2.0. So it's probably that 2.2. it's reasonable that it could be that one. This one is not 4-0 yet. Let's watch it. DEBZ. What did I say that was? It's A is located at DEB0. So there's the first number in the array. Here's the second number in the array. They're going up very slowly. There's the third number in the array. Here's the fourth number in the array. And here is the fifth number in the array. And then it's zeroed out. And I think the machine did that. So the next array would start on an even boundary. All these numbers in black on the left side are starting on the boundary shown in blue, whereas the ones right next to it on the right column in black are off the boundary. So, okay, well, you're seeing that's the activation record. Here's B, it's about ready to be executed. So N with an I says, give me information about the next thing to be executed. And it says, you're going to create array B. And do we know where B is going to be stored? Yes, we sort of do. It's at DE70. DE7. DE. Where is it? Here you are. Okay. And look at this. We're going to see this change. Right now, it starts with 4 zeros, and then a whole string of garbage over here, and then right after 9,000, and then some more garbage over here. Okay, so I'm going to execute the next statement, which will create B with its numbers. That would be in next. Okay, so now let's look at the activation record. It's here. And what was its storage? It was DE. What was its location for B was DE70. DE70. And that's a reasonable. Is that B? Let me go back and get B. Yeah, that's DE70. And what is the array B? It's some float numbers all ending in 0.5. That's the best way to describe. DE. What was the number? It was DE70. DE70. There it is. Anyway. Is that okay? And then here's this one. What was the type? Oh, we have an issue here. This is a float number. These are all floats. They're half of a quad word. So it goes out to about here. I don't know where halfway is. That's one of the numbers, and then the next number, and then the next number is a half, and the next number is a half. Okay, it's hard to read that one. So let me fix it, and we'll do it with, I think it's, let's try W. And that will show us in 30, oh, then we need more data. 37 is not enough. Let's try 80. Okay. DE70. Okay. Yeah, this is pretty good. That's a 32-bit IEEE number. And then this is the next IEEE 32-bit number. This is the next IEEE 32-bit number. This is the next one. And then this is the next one. And I think there are 5 of them, and then there are no more. So if we go back, here's it is, B5, 1, 2, 3, 4, 5. There's 5 numbers. And they alternate positive, negative, positive, negative. DE70. See that? We have to study the 32-bit IEEE, but that B is so large, it makes me think that the first bit is a 1, and that's going to be negative. That's not negative. This one is negative, and that one's not negative. And this one is negative, and then there's filler. So the next array can start on some kind of boundary. That was fill in stuff, those zeros. Oh, okay. Let's see, what's our clock say? We're almost, I gotta end it soon. You've seen examples, oh, on another day. I have to show you when one function calls another. Let's go back to that. Where's the complete stack? This one was. And this is the front end of the stack right now. It's in opposite direction from what we usually view it. This is going downward, means higher addresses. It's opposite of what I usually draw on paper. But that's the front end of the stack, and the back end, you know, this is confusing. I think it's this one. No, it can't be. It has to be on an even boundary. It's this one. I was expecting it to be 0 because it has no predecessor, but I don't, maybe I'm remembering wrong. Maybe it's like a 1 that indicates this is the back end and RBP has no predecessor, so we have to mark it in some way. All right, we'll check it out by next class and find out if that's true. But I think that's how it's working. What else do we get out of? There's one more thing I wanted to do, and then with this open in front of us. Oh, we can't do it. When we call a function, I wanted to see RIP in the stack, but this is all one activation record. We can't see. That's something for next time. We can't see it. Well, but we can do this. P/X. There are two leading commands in GDB, P and X. And X is overloaded with several meanings. Here P is an output function, an output command, and X says we want the answer in hexadecimal. And then you can look at any register. You look at RIP. The next instruction to execute, which would be to execute this instruction to fill in the data in array C, that instruction is located at address 401 4DA. That's 401 4DA is not the instruction. That's the address to the instruction. Let's actually execute this one next, and then we'll look at RIP. And see, it's moved ahead so many bytes, I don't know, 20 or 50 bytes to the next instruction. I'm wondering if, I don't know if this works. Let's give it a try. See if we can actually see the instruction code for, I think it is $401 506. Oh. Oh, it hasn't executed yet. I don't know what. Let's try. What was the number before this one? It was up here. Okay. 401. I'll give it one more try. 401 4DA 4DA. Okay. I'm doing something wrong. I've forgotten the command. If you, the idea is, if you know a memory address, can I see what is at that memory address? And I'm not getting it right. I'll try. I have one last idea. X/1 quad word in hex, size gigantic, space, $401 4DA. Oh, well, I still got it wrong. I got some, I think it's syntactically the wrong way to do it. Okay, I'll have to come another day. Nevertheless, if we, oh, here's the last resort. How about, we did P/X, P/X, $, RIP. That will tell us, no, that's just going to tell us what's inside of RIP. It's that number. How about X/, we'll do 10 of them. 10 XG. That's compiled source code. RIP is here, and it's starting to show us what's at memory, starting at that same place. And here's the first quad word, and here's the second quad word, and here's the third quad word, and so on. That's where memory is, that's where executable is stored, and it's very low numbered. This 6-digit in hex is very, it's less than 1 million in decimal. It's really close to byte number 0. Why did that start there? Okay. All right, well, we're going to explore a lot of GDB in the future. We're going to look all over memory and pick out stuff we're not supposed to look at and see what we can do with it. Anyways, I think the clock has run out on us. You're a good class for staying this long, and I'm going to stop the sharing. And Johnson's going to have a meeting at 5:15, an hour and 15 minutes from now. Or oh, we're not really. I was wrong. We're not really out of time, but I've run out of ideas to tell you about. Come and visit Johnson at 5:15 and get some help with your programming number 3. Have a nice afternoon, everybody. Take care and keep on learning. Did I?